let us continue our lectures. Recall from the last lecture I have defined what is a module, which is generalization of a vector space. The only difference is the base is not field anymore, it is a commutative ring. So, let me continue that. So, we have fixed ring A, this is a ring, and usually ring, recall that I mean a commutative ring, and this is sometimes I will keep referring as base ring. And module V is an A module. I will denote many books will write M, N, etc. for the modules, but I will keep the same notation from linear algebra, and I will keep writing V, W, etc. modules over A. And we saw that in general modules may not have basis. In general, A modules may not have basis. But to this topic I will come back after some time. The reason being I want to go back to geometry, and I will do with the minimal modules which is needed for our purpose, and then come back to it a little later. So whenever we have, like we have rings, then we have this category of rings, groups, category of groups. So similarly, the collection of A modules, A mod. This is, I want to denote this category of A modules by this. So this is the category of A modules. Once again, I will recall what I will be really still not very 100% precise. So what is the category? Category has two input data. One is objects. So what are the objects we are talking about? The objects we are talking about are the modules over this fixed ring A, fixed base ring A. So objects are A modules. And secondly, morphism between the modules. Morphisms between A modules. And together they should satisfy some obvious properties. And though with all this, it is called a category of A modules. Like we have category of rings, we have category of groups, we have category of sets, and we will keep adding some more examples, and one fine day I will define more generally what do you mean by category precisely. So this is just a working knowledge. So right now our problem is what are the morphism between the two modules. So that is the definition. So let V and W be two A modules, a map F from V to W is called an A module homomorphism. A module homomorphism if two things. See, what is the module? Module has two structures. One is additive structure in which it is an abelian group, and the other is a scalar multiplication map. So, this map should preserve both these structures. So, what does that mean? If one f preserve the addition, that means f of v plus v prime equal to f of v plus f of v prime for all v prime in v. This means it is an abelian group homomorphism, and second one is it should preserve the scalar multiplication also. That means f of a times v equal to a times f of v. This should be true for all a in a and all v in v. All right. So, that is, we should see some examples. So, an A module homomorphism is a map from V. A module homomorphism is a map from the module V to module W, which preserves addition and also scalar multiplication. Sometimes A module homomorphisms also shortly called A linear maps between V and W. And the set of all A module homomorphisms from V to W, from the module V to module W, is denoted by hom VW. This is the set of all A module homomorphisms from V into W. Okay, so to see some examples, first of all we need to see some examples of modules. So, let us see first examples, some examples. So, A is, so 1, A is our ring, then A is an A module. What is the scalar multiplication? First of all, the addition is the addition in the ring, and scalar multiplication is a multiplication in the ring. So, with this it is obvious that it is A is a module over A. When I say the A module A, that means the structure is the underlying addition of the ring, that is additive abelian group, and the scalar multiplication is the multiplication in the ring with this. So, 2, an ideal, any ideal I, or let me be like earlier, Gauti K in A is an A module. So, this is why the second condition for the ideal, that the Gauti K is closed under scalar multiplication of A, that makes this as a module. Okay. Also, the quotient ring A mod A is also an A module. I would just simply say with the natural structures. What do I mean by this? On this, for example, the addition we got from the ring to this quotient ring, that is addition in this module, and scalar multiplication is just A times any x bar is equal to A x bar. That is a scalar multiplication. All right. So, third one is very important. Remember, from a ring A, we have constructed the polynomial ring, say let us say in one variable. This is the polynomial ring. Over A. That means the polynomials have coefficients in A, and this is a ring by usual addition of polynomials and multiplication of polynomials. And this one, then Ax has the natural structure of A modules, where the multiplication, where the addition in the polynomial is usual polynomial addition, and scalar multiplication of A on A is precisely you multiply a scalar by a polynomial, as usual you multiply two polynomials. So, this is one. So, also fourth one can also consider A as an Ax module. So, for this what do I have to do? I have to give you what is the scalar multiplication of the polynomial onto this given ring. So, well, the additive abelian group is the abelian group of A, the ring A. So, this is the given abelian group, and if I have a polynomial f with coefficients in A, and if I have any scalar A, how do I multiply f with A? This is by definition, you can take f of 0 times A, and now it is easy to check that this is a module, A becomes an Ax module. This is little bit artificial and this is not the unique way. So, you can have several A module structures, several Ax module structures on the ring A. So, this is not unique and this is also not very natural. Alright. So, the next one 5. Now, if you take the ring A to be Z, then any abelian group has a natural structure of Z module. So, if you have any abelian group G plus, how do you define a scalar multiplication of Z on G? That is usually how you multiply. So, if this is n times any G, this is Ng. And what is Ng by definition? This is G plus G plus G n times, if n is bigger or equal to 0, and otherwise it is minus G plus minus G minus n times if n is negative, where minus G is the inverse of G in the group G. So, this is minus G equal to the inverse of G in G, because it is abelian. So, with this is also natural. So, with this so the theory of abelian groups is identical with the theory of Z modules. And also the homomorphisms, home groups G prime, this is same as home Z G prime. So any abelian group homomorphism is a Z module homomorphism, and any Z module homomorphism is an abelian group homomorphism. This is way. So if you would have studied modules over arbitrary commutative ring, then the study of abelian groups is included in that. So that's one. Okay, now next one. Now recall very quickly submodules. Like for rings we have ideals. So for modules we have submodules and quotient modules. Let us recall this quickly. So we have a fixed ring A, base ring, and V is A module. Then when do you call a subset to be a submodule? So a subset V prime of V is called an A submodule of V. Sometimes you drop this in the notation A, because once you have fixed a ring, then you don't have to write that, but it is maybe better. If the same addition, so V prime with plus is a subgroup of V plus, and the scalar multiplication restricts to V prime, and A times any V prime belongs to V prime for all A in V, A in A, and V prime in V prime. That means if I restrict the structure of V to V prime, that itself becomes an A module. Then it's called a submodule. Now for example, ideals in a ring A are precisely A submodules of the module A, of the A module A. That is precisely, because ideals are the subgroups, and also restriction of a multiplication goes inside. It induces a scalar multiplication on the ideal A. Okay. So how do you find submodules of a module? So this is 1, 2, given any element, V in V, how do I generate a submodule out of this V? So I want to make submodule. So you take obvious notation, the subset AV, these are all A multiples of that given V. So this is by definition as usual A times V, where A is varying in A. This is a subset of V, is clearly an A submodule of V. So if you have two elements here, you can add, you can subtract, and again you will get the elements of the same type, and also multiply by any scalar A and you get again element of the same type. So, it is a submodule, and this is the smallest, this is the smallest submodule of V containing small v. So, that gives again for us to imitate what we have defined in case of a ring and ideals. So, very quickly, suppose I have a finitely many elements V1 to Vn in module V, then what is this? Then the smallest A submodule of V is precisely this set A V1 dot 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 plus A Vn. This is by definition all A linear combinations of V1 to Vn. So, A1 V1 plus 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 An Vn, where A1 to An are elements in the ring A. Again, it is very easy to check, it is smallest, it is very easy to check, it is a submodule, and this submodule is said to be generated by V1 to Vn. It may have different set of generators also. For example, let me write one example. Let us take A to be the ring Z and elements 4 and 6. 4 and 6 are elements here. So, what is the submodule of Z? Z submodule of Z, Z submodule of Z generated by 4 and 6, 4 and 6 is Z4 plus Z6. But this is also same as Z2, Z2. See, this one is obvious, 4 is a multiple of 2, 6 is also multiple of 2, therefore, all elements here are multiples of 2. So, Z2 is one submodule which contain both these and therefore, it contains a submodule generated by that. Conversely, 2 you can write as a combination of 2 and 3, 4 and 6, 2 equal to minus 4 plus 6. So, therefore, this containment is also clear. So, therefore, it is, so 4 and 6 is a generating set for this submodule and 2 is also generating set. So, generating set is not unique usually, this is a generating set. This is also generating set. When does one call a set to be minimal generating set? If you already know linear algebra in a good setup, then you can guess most often and you can write your definitions correctly, examples correctly. So, when do you call a set of generators of a submodule to be minimal? That means you cannot drop any one of them. So, I will make that as a next definition. So, before that let us write, so again there is nothing special about finitely many elements. So, if I have a family Vi, Vj, Vi, I in V, then what should be this summation I in I A Vi. This is by definition all the finite sums among Vi's, A linear combinations among Vi's. So this is summation over J, J in J, and J is the finite subset of I. This is finite. And then we are taking some elements in AJ, Vj, where J is in J, and the J is the finite subset of I. Obviously, this is a submodule by the same checking, and this is the smallest submodule which contain all the elements in Vi. So that's it. Okay. Now when do you say a module is finitely generated? So definition: an A module V is finitely generated over A if there exist finitely many elements V1 to Vn in V such that V equal to A V1 plus A Vn. So that means V is the smallest submodule of V which contain all these V1 to Vn. So again examples. The A module A is finitely generated. In fact, it is cyclic A module. What does that mean? That means it is generated by one element. Since A is generated by 1, or it is also generated by any unit. So in particular Z is 1 is also generator of Z, and minus 1 is also generator of Z. These are the only two generators of the Z module Z. These are generating sets. It has also, of course, there are many generating sets, but these are the smallest generating sets. These are minimal generating sets. But of course, 2, 3 is also minimal generating set. Because you cannot drop 2, you cannot drop 3 also. So it is a minimal generating set. So among the minimal generating sets, the cardinalities are not same. You see, that was not happening in case of a vector space. In a vector space, all minimal generating sets have the same cardinality. So this is not true for modules. Alright. In fact, you can write down given any integer r, any natural number r, there exists A1 to AR in Z such that the set A1 to AR is a minimal generating set for the Z module Z. This is very easy to check. Easy to check. Well, it is not all that trivial, but it requires some work. Alright, so things can become complicated. Now, some example of a module which is not finitely generated. So, to look at Q plus rational numbers with addition. So, this is a Z module. And Q is not finitely generated. Z module. Let me sketch the proof. So, sketch. So, suppose there is a finite generating set. What does that mean? The generating set consists of some rational numbers. Suppose that x1, xn are rational numbers and they generate Q. So, these are rational numbers. So, they have a numerator and a denominator. So, I can write xi equal to ai by bi, where ai, bi's are integers, bi non-zero, I equal to 1 to n, 1 to n. So, note, if they generate, if xi generate, then these new guys a1 by b, I make the same denominator, I make the common denominator. So, I simply I will write, we may assume all bi's are equal to b. Simply multiply up and down by take all b1 to bn and multiply up and down, and that we are not changing xi, so it will same generate, the denominator is common now. And now, so that means what? That is, we are assuming a1 by b, a2 by b, an by b, this generates Q. But if they generate Q, then 1 by b also generates. That is obvious, because if 1 by b is there, this a1 is an integer. So, a1 by b is also there. We are allowed to take z linear combinations. So, this is also generated. But then if this generate, what does that mean? That means any rational number is a multiple of z multiple of this b. So, in particular, one by b square will be some a by b with a in z. But what will this mean? This is equivalent to saying multiply across. So, that is, and cancel b. So, b equal to a times b square. So, b equal to a times b square, but that is if and only if b is non-zero. So, this is b is non-zero. So, this, So that is equivalent to saying cancel one of the b, 1 equal to ab, that is equivalent to saying b is a unit in z. But the units in z are precisely plus minus 1. So b is plus minus 1. So you can't, no matter what you do, you only get integers with the b is in plus minus 1. So if you multiply any element of 1 or minus 1 by integers, you will get only integers. You will never get 1 by p, for example, half. So then half is not an element in the submodule generated by b, because this submodule is z only, 1 by b. This submodule is z only, and therefore half is not there. Therefore what we approved is z times 1 by b. This is a submodule generated by 1 by b of q. This can never be q if b is plus minus 1. So that proves that q is not finitely generated z module. Okay, one more example. One more very important example we will use all the time. So now take A is arbitrary ring A, commutative always, and the module V to be the polynomial ring over A in one variable. This is the polynomial ring over A in X. We have seen that this is a natural A module structure, and I want to say that first of all let us write one generating set, then 1 x, x square and all the monomials in x, x power n, etc. This is a generating set for the A module Ax. Because any polynomial is a linear combination of this. This is a countable set. So therefore in the notation, so that is Ax equal to summation over n A x power n. This is the smallest submodule generated by that. But this is a minimal generating set. This is a minimal generating set for Ax as A module. That is also clear, because if you drop any one of them, you can never get x power n in terms of the remaining one. So that I will not check this, I will just say check, precisely check this. So in particular, so not in particular, moreover Ax has no finite generating set. Because if it has a finite generating set, let us call them F12, Fr. If these polynomials generate Ax, that means what? That means if I write A F1 plus A Fr, this is Ax, then I should get a contradiction, a linear combination of this. So you see these guys have some degrees, d1 to dr, they are the degrees of F1, this is degree of Fr. Now choose any n. In n, choose n in n with n bigger than everybody for all I. Then x power n is an element here, but you cannot write it as a linear combination of F1 to Fr, because maximum you will get d1 to dr degrees here, and this degree is n. So that is not possible. So this is not, this does not belong to LHS. These belong to RHS, that is, it is a polynomial of degree n, but it cannot belong here. So, okay. So, with this we will continue. Now, the next half I will introduce algebras, and then after that we will be ready for more geometric setup. So, and whenever I need it again, I will come back to the study of modules later. All right. So, thank you, and we will meet after the break.